What is the golden ratio? It's the ratio of sides of a special rectangle, a golden rectangle. If you cut off a square, the leftover rectangle has the same proportions as the original rectangle. That is, a plus b over a equals a over b. This ratio is often represented with the Greek letter phi. It has been claimed that golden rectangles appear in ancient Greek architecture and some famous artwork, but this is not borne out by measurements. The Greeks' interest in this quantity probably started when they considered the regular pentagon. If the side length is 1, then the length of a diagonal is the golden ratio. Closely related is the pentagram. If the shortest of these lengths equals 1, then the other lengths are powers of phi. Over 500 years ago, the Renaissance thinker Luca Pacioli was also bewitched by this ratio, so he wrote the book The Divine Proportion. Illustrated by his friend Leonardo da Vinci, the book studies various geometric solids and the golden ratio's appearance in architecture and the human body. Some artists have explicitly embraced this ratio, such as Salvador Dali, where the canvas for his painting, The Sacrament of the Last Supper, is a golden rectangle, and the windows in the background are framed by a dodecahedron, a regular solid with 12 pentagonal faces that also connects to the golden ratio. I don't want to argue for or against the golden ratio in nature and art, but rather show the many cool ways where the golden ratio appears in mathematics. First, what is the value of the golden ratio? Remember that it is defined as the quotient a over b. By rewriting the equation and doing a bit of algebra, one finds that phi satisfies this quadratic equation. We use this to solve for phi and then find a similar expression for 1 over phi. The appearance of the square root of 5 should not be surprising because of phi's relation to the pentagon. In fact, this connection explains why phi can be written in terms of trig functions. People today often first encounter phi with its connection to the famous Fibonacci numbers. By taking the ratio of consecutive Fibonacci numbers, the limit of these ratios approaches phi. But this isn't unique to the Fibonacci numbers. The Lucas numbers, named after Edouard Lucas, are also built by adding 2 terms to get the next term. The ratio of consecutive Lucas numbers also approaches the golden ratio. But the plot thickens. Both the Fibonacci numbers and the Lucas numbers can be written in terms of powers of phi. These are called Binet formulas. These formulas imply that powers of phi, with or without dividing by the square root of 5, are increasingly close to integers. As a bonus, here are 2 formulas that connect powers of the golden ratio to the Fibonacci numbers. Okay, let's get back to geometry. A golden rectangle can be progressively dissected into squares whose side lengths depend on phi. Some people also like to draw the golden spiral. But how can we construct phi geometrically? Start with 4 1x1 squares. Connect these 2 corners, then construct this circle. The length of the red segment is phi. Can you see why this is true? There are other ways to get phi geometrically. Here's a way with 2 squares and a circle. Here's a way with 3 squares and a circle. Here's another way with 3 squares and a circle. Or here's a way to get phi with 2 regular pentagons. Or switch to these 2 sides. The golden ratio is also used to make kites and darts, which fit together perfectly to form Penrose tilings of the plane. Moving to 3 dimensions, 3 orthogonal golden rectangles can be constructed with the 12 vertices of a regular icosahedron. Let's connect phi back to numbers. Suppose we look at these nested fractions with 1s. Working them out shows that we have ratios of consecutive Fibonacci numbers. If these fractions continued forever, we have that the limit is the golden ratio. A way to see this without Fibonacci numbers is to label the continued fraction as x. Notice that the continued fraction in the red box is also x, leaving us with this simple expression. We can now solve this equation and show that x equals phi. Instead of nesting fractions, suppose we nest square roots. Borrowing the same trick, let x be the expression with infinitely many square roots, and recognize that the red box captures the original expression, so x satisfies this formula, which in turn produces phi. Here's a different connection to numbers. We say that the floor of a number is what you get when you round down. So for example, the floor of 9.8 is 9 and the floor of pi is 3. Now let's look at the floor of each multiple of phi. Calculating the first few values produces the sequence 1, 3, 4, etc. But what about the numbers we skipped? 2, 5, 7, etc.? It ends up that these are obtained a similar way with the floor function and multiples of the number phi over phi minus 1. This is a special instance of Beatty's theorem. Okay, one last beautiful formula. This eye-catcher connects an infinite series that involves the golden ratio to an infinite continued fraction involving the Fibonacci numbers. It's so nice that it almost puts a smile on your face.